All right. Radioactivity. This is what we're starting, radioactivity, all right? Now, there's a lot of stuff about this you know. This lady right here, super famous. You don't have to write her name down because you've heard it before, Marie Curie. She's got elements named after her. She's responsible for 3 of the elements on the periodic table, and what I mean is she named 2 of them, and one of them's named after her. She's a genius and a really interesting person, Marie Curie, okay? She studied radiation, and actually her studies of radiation killed her, okay? Radioactivity, this is what it is. When the nuclei of atoms begin to fall apart. A lot of atoms are unstable. And the reason they're unstable is they have a disproportionate amount of neutrons. You would think, since neutrons were neutral, that they wouldn't matter. But that's far from the case. Having the correct amount of neutrons in the nucleus of an atom can determine if that atom will last for a millisecond or a million years. There's a lot of math that goes into the stabilization of an atom, and it's not just based on the protons and electrons. Protons and electrons determine ionic bonding, and we played cards and we wrote chemical formulas, right? Electrons control covalent bonding as well because they're being shared. But as far as how long an atom will last, or that is it radioactive or not, that really has to do with the neutrons, okay? This, I know, just looks like a blob to you, but a long time ago, a scientist, I believe it was Röntgen, a long time ago, a scientist had some uranium salts, okay? And we were already using uranium salts at the time. He had a little bottle, a little glass bottle about like this, and he put it in his desk drawer and closed it for the weekend, all right? He just happened to have set the bottle down on some photographic paper. You know, like old style film, where you used to be in a dark room and you would have to develop the film. Do you guys know what I'm talking about? Well, he's happened to set his bottle of uranium salts down on a set of photographic paper, closed it in the dark. When he came back on Monday, the story goes, the photographic paper had developed a picture of the bottle. And this is where the salts were in the bottle, all right? This little ring here, I think, is where the neck of the bottle was, and the glass is a little bit thicker. All right? Anyway, that's it. And he's like, hey, these atoms are doing something. They have to be giving off, these uranium salts have to be giving off invisible energy. Because, and this invisible energy must have rays of energy like light, because they developed the paper as if light had hit it. Does that make sense? And he was right. There's 3 different ways that atoms fall apart. And those 3 ways are called alpha, beta, and gamma radiation. There's actually 2 types of beta radiation. We usually just cover one in physical science. In case you're wondering, alpha, beta, and gamma are letters from the Greek alphabet. I believe they're the first 3 letters, like ABC. But I'm not sure. I didn't take Latin in high school. Do we even offer Latin here?
No.
Yeah, it would be an excellent course to take. I remember not understanding that in high school. But taking Latin would give you the ability to understand a lot of words you've never seen before. Does that make sense? Because you can see their root. Cough, cough.
It is the third letter.
Huh?
It is the third letter.
Oh, thank you. All right, now I feel a little bit bad. All right, alpha, beta, gamma. So here we go. Alpha radiation, we're going to draw this as a picture. Just right the top. Just right the top. When 2 protons and 2 neutrons are emitted from the nucleus. All right? This is what alpha decay is. And I'm just going to show you a little example of this happening. Okay? Whoopsie. Hello. I'm going to show you a little example of this happening. You just need to write this. 2 protons and 2 neutrons are emitted from the nucleus. If you're watching this at home, you've already taken notes, you can just fast forward through this part. That's what YouTube does. All right? Okay. Now I'm going to show you a picture of this. And we're going to zoom in on an atom. Right? So imagine this. We're going to zoom in on a very large and unstable atom. We're zoomed in so far with the microscope that this is the nucleus and we're just catching the nucleus, all right? We're going to say this nucleus has 1, 2, 3, 4, 5, 6, 6 protons. Who would this be? Carbon. That's exactly right. Does that make sense? Now, normally, carbon, since we'll draw a card of carbon, carbon's number 6, and it normally has a weight of 12, which means normally it would also have 1, 2, 3, 4, 5, 6 neutrons. Does that make sense? This is the most common isotope of carbon, and it is very, very long lasting. It is stable. This version of carbon is not considered to be radioactive. All right? But there's another version of carbon that is very radioactive. It doesn't mean that it's dangerous, and that's called carbon-14. It's called carbon-14 because what it says? Bam! Bam! It's got 2 extra neutrons. So now this weighs 14. It's got 6 protons and 8 neutrons. Does that make sense? Everybody with me? Now, carbon-14 is an element that typically decays into nitrogen. But we're going to make this carbon crazy. We're going to make it carbon 15, 16. Now we've got carbon 16. This carbon normally has 6 neutrons, and now it's got 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now it's got 10 neutrons. This thing is out of whack. Does that make sense? So it starts to break apart because its electromagnetic math is not working out. And the atom starts to crack, the nucleus starts to crack, and all of a sudden it spits out a radioactive, pew, pew. You like my sound effects? Spits out a radioactive particle, and this is what the particle would look like. It would be a large particle consisting of 2 protons and 2 neutrons. This is called an alpha particle. Alpha particles you can think of as like beach balls. And you're like, why would we think of them like that, Mr. Perkins? Because as far as particles go, alpha particles are really big. As far as radioactive particles go, alpha particles are really big. And they're also easy to stop. So doesn't that remind you of a beach ball? Something that's very big and easy to stop? If I threw a beach ball at your head, don't you think you could stop it like this? Because it's a beach ball. That's how I want you to think about alpha particles. Now, if the nucleus spits this out, you have to also realize that 2 neutrons and 2 protons are now missing from the nucleus. Does everybody agree with that? So after this alpha particle has been sped out, after the alpha particle has been grotesquely spat out, now this is a different atom. What atom is this on the periodic table? It's number 4. Who's number 4? Beryllium. And then how much would it weigh? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. This would be beryllium 12. What's beryllium normally weigh?
9.
9. Do you think this would be stable? No. So this could break apart again. That's how radiation works. That's radioactivity. These nuclei break apart until they end up being something that's stable. Then they last for millions of years. Does that make sense? All right. Now the next note you need to write is this. Let's talk about this alpha particle. You should draw this alpha particle on your paper. And let's talk about it. How much would this alpha particle weigh if we weighed it? That's right, it would weigh 4. It would have a mass of 4. Everybody agree with that? What's the atomic number of this alpha particle? How many protons does it have? 2. So it's 4 over 2. And now let me ask you a question. Whose nucleus is this? Look on the periodic table and find an element that is number 2 and has a weight of 4.
Helium.
Helium. This is largely how helium is made. This is largely how helium is made. From the alpha decay of unstable atoms inside of the Earth. This is where we get helium from. We don't make it in a lab. It occurs naturally through alpha decay inside the Earth. And then the helium atoms come up, and they get trapped in underground caves, and we drill for them, and then we have helium, and then we throw a birthday party. That makes sense? Here's the only catch. This isn't actually helium because there's no electrons. Right? So it's 4 over 2 helium plus plus, or plus 2. Right? The next thing that's important is we can also, instead of saying 4 over 2 helium plus plus, it's an alpha particle. So we very frequently just use the Greek letter, and you should write this down also. Instead of putting a helium there, we make like an alpha symbol. 4 over 2 alpha plus plus. So redraw it like this. Write a 4 over 2 alpha plus plus. That is an alpha particle. And what you just saw happen here was the radioactive alpha decay of a carbon, what was it, 16 nucleus. So all of this stuff makes sense. Like it makes physical sense. It's really simple math. If this weighs 4, then this just got 4 lighter. Does that make sense to everyone? So that process is called alpha decay. I want to write this picture that I just drew for you. I want to write it as a really simple math formula. I already felt some of you frown, but you won't when you see how simple it is. Watch this. The first nucleus we had was 16 over 6 carbon. Does everybody agree with that? It was, or another way to say this is carbon dash what? 16, that's right. Carbon 16. So this is a carbon 16 atom. And then it's going to, we're going to draw an arrow here saying, hey, something's happening to it. Carbon 16, this arrow says it decays. It decays by spitting out an alpha particle. An alpha particle is 4/2 He++. And what's the other thing that would now be left over? I know some of you are still writing, so I'm going to wait 1 second. Right? So watch how easy this math is. Ready? This is easy math. I'm calling on you. At first, it was weighed 16. And now it's broken down into two different things. One of them weighs 4. How much does the other one weigh? Blank plus 4 equals 16. Or 16 minus 4 is what? 12. Okay? So now the other particle weighs 12, and there were 6 protons, and then it lost 2 protons. So how many protons are here? 4. 4. And what is the symbol, Zamir, for number 4 on the periodic table? B, E. This is pretty simple, y'all. 16 minus 4, because it loses the alpha particle, is 12. And 6 minus 2 is 4. This looks way more technical than it is. This is, you want to write down, probably just right over here, this is alpha decay. This is the alpha decay of carbon 16. And then to end this little video lesson for people at home, this is the chemistry way you would say it. You would say that alpha decay of carbon 16 produces an alpha particle and beryllium-12. Does that make sense? That's it. That's alpha decay. We'll cover beta in the next video.